get the points. Okay, so remember, if we are using our calculator, we put those in, and then we go to our stat, calculate one variable statistics. List should be L1, frequency list is just blank, and we get this. So our X bar is our mean, S is our standard deviation. So I'm going to jot that down. So what did you guys get for your mean? 30? Okay, so 32.14. The median. How do we find median on here? Yep, if we go down it says MED, so that was 32.5. Standard deviation, the S was 6.175. Okay, you'll notice I asked for interquartile range. Okay, if I scroll down, do you see IQR as anything here? But yesterday we said interquartile range can be found by doing what? Q3 minus Q1. Did this tell me my quartiles? Yeah, it told me quartile 1 is the Q1. The median we said yesterday is the same as second quartile, quartile 3. So if we do Q3 minus Q1, 38 minus 28, we get an interquartile range of 10. Now let's do this same thing with our new data points. So all we have to do is go back to our list. And at the bottom, we are going to add in one more point. And it said this car was going 100 miles per hour. So I'm going to add in a 100. So that was back to our stat edit. And now we want to recalculate everything. So stat, calculate the one variable statistics again. And now it tells me my X bar, my mean was 36.67. The median is 33. Standard deviation, 18.504. Interquartile range, so Q3 is now 39 minus 28, which is 11. All right, so if we compare the mean and the standard deviation, those both changed by quite a bit, didn't they? So my mean, this was a big change. Standard deviation, that was huge. What about the median? Did that change much? And what about IQR? Okay, so think back to what we talked about before. I threw in one large value, and it had a big impact on my mean, but not my median. What did we call that? Yes. So the median is more resilient. Okay, it's got more resistance there to those extreme values. Now we're seeing the same thing with standard deviation and interquartile range. Standard deviation, or measure of spread, a big value really has a huge impact on that. Interquartile range is not. So that means if your data is really skewed, that would be a case where you might want to look at your interquartile range. If it's nice, symmetric, bell-shaped data, we don't have those extreme values, then our standard deviation is going to be better for us. And so that's what I said here, kind of what's the best measure. So if you have symmetric data, your mean and standard deviation is the best option for describing your data. But if your data is skewed, either left or right, the mean and standard deviation are no longer very accurate. So in the case where you have skewed data, your median and your interquartile range are going to be better. This might be a great multiple choice question on the next test, just kind of knowing when to use what. So if it were me, I'd probably jot down, this is basically the best measure. So if your data is symmetric, you want to give me the mean and standard deviation.
You need to write down central tendency.
No, you don't have to. If your data is skewed, the median and interquartile range would be better. Any questions on that? What's better with? So the last piece in this section is outliers. You know, it's easy for us to look at speeds in a construction zone and say, 100 miles per hour, that is really far out. That's an outlier. That value is extreme. But if I had said 50 miles per hour, would that be an outlier? Or would 57? We don't know. It's kind of a gray area. So we need a cutoff that kind of tells us what is an outlier and what's not. What is an extreme value? And so to find those, outliers are just our extreme values. Those are any points smaller than what's called the lower fence. Or greater than the upper fence. And these calculations are on your formula sheet, so you don't have to memorize what they are, just like all of our other things. Lower fence is quartile 1 minus 1.5 times the interquartile range. And the upper fence is quartile 3 plus 1.5 times the interquartile range. So kind of the agreed upon cutoff is if your quartile, if 1.5 standard deviation or interquartile ranges are beyond that. So for the lower one, quartile 1 minus 1.5 IQR, upper one, quartile 3 plus 1.5 IQR. So basically we find those values and see if there's anything fall outside of that window. Everything between those numbers is good, anything outside would not be. So if I wanted to check my speed data for outliers, let's use that set with the 100 miles per hour. Okay, then what was the quartile 1 from that last set of data? It's probably still on your calculator.
39.
Quartile 1? 28. Quartile 3?
39.
And the interquartile range was 11. So my lower fence is quartile 1, so 28 minus 1.5 times the interquartile range. 28 minus 1.5 times 11. We get 11.5. Did we have any values smaller than 11.5? No. So we don't have any values that were too low. To find the maximum, we do the upper fence. So quartile 3 plus 1.5 times the interquartile range. that gives me 55.5. Did we have any speeds that were bigger than 55.5? Yes. If we look at that last set of data, there was only one. About 100 miles per hour is an outlier. And in fact, 50 would not have been, but 57 would have been an outlier. So this basically just gives you the acceptable values that are not considered too extreme. They would be outliers. All right. Questions on that? Let's just try an extra example, kind of reaching back to yesterday. So take a second, read this, and see if we can figure out what to do. What am I asking you to do? Which race is he better at? So we have the 100 meter. And the 200 meter. Okay, if we organize our information a little bit. So in the 100, the mean is 48.62. Standard deviation.
This is so pedantic for the view, not the Xbox.
Yeah, we could do it that way if you want to think of it as. Yeah, it won't matter in this context, but sure, because it is all college students. Standard deviation 0.98. And what was his particular speed? In the 200 meter, the mean for that race was 106.58. The standard deviation of that race was 2.38. And his speed, 99.32. And I want to know in which race is he better. So what do I have to do in order to be able to compare two different sets of data? The z-score. That's what we were working on yesterday. So remember, your z is our value minus the mean divided by standard deviation. So on the 100 meter, his z would be his value minus the mean divided by standard deviation. I told you we typically go to 2 decimals on a z. Not that it would be wrong if you gave me more. So for the 200, his value minus the mean divided by standard deviation. Okay. Why are both of these z's negative? Faster than average, which is a good thing in a race, right? So if I'm asking which one is better, yeah, you want the one that is more negative, smaller number, because that means he was more fast in that race. So this is the better race. Because he was more below average on that one.
Could you not just look at his two races like up and down that? The one that's.
Not necessarily, because standard deviation could have an impact on that.
Alright.
So that's what we were doing yesterday. Do we need another z? So from here, it's up to you guys.